1945, my grandpa started dairying. It's been a family operation. We have about 500 milk cows plus all our young stock. We have about 1,000 animals. In the past, the manure came off the cows, went in the lagoon, later on pumped out on the fields.
And naturally occurring bacteria will convert that to methane gas. And methane is a greenhouse gas that's 25 times as powerful as carbon dioxide. Methane releases from these lagoons and from these dairies is a big contributor to greenhouse gas.
We looked at it as an opportunity to be able to stay in the dairy industry in this area, both from an environmental standpoint and an economic standpoint.
We take the natural bacteria that's going to occur anyways in the lagoon and we put it into an engineered system.
So this is the digester here. It's a little over 1 million gallons of manure. We're feeding in a combination of manure and food waste. And we put in about 50,000 gallons per day. Once the material goes into the digester, we heat it up. It flows through the system for the 20 days. The bacteria produce methane gas, which floats to the top and then comes out of the digester, flows through a pipe into the building. We run it through the engine and produces electricity.
The gas making the bubbles in these green tubes comes from the power plant's smokestack. And the green stuff is algae. Ancestors of the algae here once grew in the ocean, but now the microscopic plants are feeding on the flue gases and growing in the sunlight.
They just drain, use gravity.
Just drain it out.
It's like a cow. They take a little bit of milk from the cow, and you leave enough there for the, for the new generation to catch up.
The algae in the buckets have done a job power plant operators usually have to install expensive pollution control equipment to do. And that's to remove nitrogen oxides from their stack gases. The algae have also consumed most of the carbon dioxide, or CO2.
So
now this has a lot of bad stuff in it. You wouldn't want to...
No, actually not. Once the CO2 is turning into organic carbon, there's nothing bad in it.
You mean a person could eat this?
Yeah, actually we start every morning.
I'm shocked that the producers haven't made me eat this.
Listen, I want to tell you something. We start every morning with a glass of algae drink.
Get out of here.
Listen,
I don't believe that.
Listen, you can get it in Whole Foods. It's called the Green Machine, or there's all kind of generic names for it. Basically, algae drink. It's good for you. It's a health product.
So after the algae eats all that bad stuff,
yeah,
it's just a nice piece of algae.
Because the chemistry changes.
One renewable raw material will be part of these improvements. It's the algae. The biomass of this plant is used in breakthrough developments throughout various industries: cosmetics, food and dietary supplements, water recovery, and medicine. But how do you grow this microalgae? In highly efficient tubular glass systems called photobioreactors. These engineered systems deliver results that continue to astound even scientists. The reactor provides optimal growth conditions so that high-yield algae are grown in only 7 days.
Chemical species. Techniques are based on mid-infrared laser absorption spectroscopy, which can answer such questions as what species are present, as well as what is the concentration. This is accomplished by exploiting the unique molecular fingerprint of different chemical species and is applicable to atmospheric molecules with fine spectral features as well as larger molecules with broader features. A basic device uses a tunable laser which probes a gas sample. Molecules absorb the laser at specific wavelengths and impart their unique spectral fingerprint in the measurement. By comparing this measurement to a library, it enables both identification of chemicals that are present as well as determination of the concentration.
My name is Federico Capasso. I'm professor of applied physics in the School of Engineering and Applied Sciences at Harvard University. I've been there for the last 8 years after a 30-year career at Bell Laboratories. I'm very much interested in the history of technology and science, and if you look back at all inventions, basically the ones that make it commercially, typically, there's usually a minimum of around 10 years. I mean, there are exceptions, of course. And I think the QC laser has started, in fact, to take off commercially 10 years later, 2004. Now there is almost around 20 companies. I think that the next decade is going to be really the decade of chemical sensing. Many are going to be enabled by the quantum cascade laser, but also for pollution monitoring. Most important, I believe, also areas like combustion diagnostic, medical diagnostics. We have shown that combining laser technology like quantum cascade laser, but not only QC laser, with plasmonics can deal with a very interesting thing. We have shown that we can shape the beam of laser. So we have made multi-beam, multi-wavelengths quantum cascade laser. I think this is a unique feature, okay, the ability to have a laser to simultaneously launch multiple wavelengths in different directions.
So unmanned aerial vehicles, we've been working on this for about 15 years now, and this is the smallest robot we've built. It's only 11 centimeters tip to tip, has a max speed of about 6 meters per second. The inspiration for this really comes from nature. So if you look at honeybees, for example, they're extremely small, they're very maneuverable, and that's basically what you see in these videos. You see the robot going through these planned obstacles. So if the robot knows where the obstacles are, it can plan these minimum snap trajectories at a fraction of a second, often 20, 30 times a second. And it doesn't matter if the obstacle is moving. If the robot knows how the obstacle is moving, it can determine how to plan trajectories to go through the obstacle. Some of you may have seen videos of birds fishing to catch their prey, and this is amazing. You look at this bird coordinating its flight, its vision, and so on, and its claws, and we try to do the same thing with robots. And so here's a robot fishing for Philly cheesesteak hoagies, and it's able to pick that out. So again, we focus on the split-second timing, coordinating vision, coordinating arms, coordinating hands, and flight as you fly through complex environments. And then finally, work of Sarah Tang, where she's able to use this framework to think about transporting suspended payloads whose length is more than the height of the window. But ultimately, we're interested in solving some real problems. The first problem area that we're very excited about is agriculture. So if you look at the challenges facing society, I think you'll quickly come to the conclusion that water and food, and actually these challenges are related, are our number one challenge. The efficiency of almost all production systems in the world has gone up over time, but for food it's actually going down for a variety of reasons. So one thing we're really interested in is trying to see how we can use robots to monitor and tend crops. And here's our robot flying in an apple orchard carrying all kinds of sensors, and they're able to, in this environment, do fairly simple things. So on the bottom left, they're gathering infrared information. On the bottom right, they're building three-dimensional maps of apple trees. And in the center, they're computing an index called NDVI. So each of these pieces of information is useful in order to assess the health of a plant. So for instance, if you know something about the size of the plant, if you have a three-dimensional map, you can fly by that plant week to week and measure the state of growth, and you can estimate how healthy it is. If you look at this NDVI, the central thing, that essentially tells you something about the vigor of the plant. Something even more basic, flying past these plants, we can count apples, and we can estimate the yield on the plants, and helps them plan for downstream picking, harvesting, and then shipping. Something quite basic with every manufacturing facility has, but farmers don't have.
For high-tech industries, the drive to miniaturization is immutable. As conventional manufacturing technologies fail to keep pace, additive manufacturing is emerging as the disruptive alternative. Microfabrica is uniquely positioned at the forefront of these converging trends, with the only high-volume production microscale additive manufacturing platform in the market. Like 3D printing, Microfabrica produces highly complex, three-dimensional structures directly from a digital model.
A design for a device that helps clean by deploying hundreds of tiny flying robots was the winner at a recent Electrolux Design Lab competition. The device is equipped with 908 tiny flying robots that can be powered by solar technology. Each robot cleans by releasing a drop of water and fly back to their stations to recharge. The technology was designed by 23-year-old Adrian Perez Zapata, who said he was inspired by the controlled flight of bees.